So this talk is about the numerical simulation of laser processes, including melting and polishing. This is a joint work with Professor Marco Picasso from EPFL and Alexandre Masseret and Julien S. from Ecosystem, which is a startup company in Switzerland. And this is partially funded by UNOSUIS. The outline of the talk is very classical. First, we are going to talk about the model and the equations. Second, we are going to talk about the algorithm, the method. And third, I will show you a couple numerical experiments. The motivation is obvious. We want to do laser polishing. So typically, by passing a laser on top of a rough surface, being able to decrease the roughness and polish it. This sketch is quite classical here, where you have an initial roughness, and then the laser passes, it melts the metal, so there is a melting pool that re-solidifies in the wake, and then create a polished surface. Our aim is to do the simulation of such processes and create a standalone solver that couples the heat effect with the fluid flow effect. So this is typically a multiphysics domain in a multi-domain approach. So what do I mean by this? So it's a multiphysics. Why? Because we have an incompressible fluid, typically in the melting pool, together with the thermal effect, and free surfaces. So in red, you have the variables, velocity and pressure, that are related to the fluid flow. In blue, you have the enthalpy and the temperature, the variables that are related to the thermal effect. And in green, we are going to track the free surface, so that means the deformation of the metal on the top due to the laser, with the so-called characteristic function, phi, that is able to track the free surface. And we are going to do it in a multi-domain approach. So typically, we are going to solve the heat equation in the large piece here, the big gray piece, but in order to solve the fluid flow, we are going to zoom only in the subdomain here, the white box that is called lambda. So now we have our variables, we need our equations. First, we have the equations for the incompressible fluid flow, and we are going to consider the Navier-Stokes equation, or the first box here, with the additional reaction term, that is the coupling with Darcy, that will allow us to penalize the velocity in the solidified metal. And this will be solved in the so-called omega t. And omega t is the domain, but zoomed on the smaller domain, on the smaller box. Then we are going to solve the so-called volume of fluid method. So this is an advection equation that allows us to track the characteristic function of the fluid. And this will also be solved in lambda, so that means in the small box. And that will allow us to be able to track in time the evolution of the free surface. And finally, we are going to move to the heat equation. And for this, we are going to expand the domain. So we are going to work in omega t union sigma, so the big piece. And we are going to solve the heat equation with transport equation. And you can see that these equations are actually coupled. If you know the velocity, you will know the transport effect on the heat equation, and vice versa, if you know the temperature, you will be able to calculate this coefficient alpha, that is the penalization reaction term. Talking about alpha, so alpha is actually looks like this. And it penalizes the velocity, so that the velocity equal to 0 in the part of the domain where the metal is solidified. We are going to assume that the density and the viscosity are independent of the temperature. And this is an assumption that mostly rely on the fact that there is no real mushy zone in such processes between the melting pool and the solidified metal. And we are going to need some physics to link the temperature and the enthalpy in a very classical way, and vice versa, the enthalpy, the enthalpy with the temperature. Finally, we are going to have a free surface on the top. And this free surface, there will be a force on this interface, that is actually composed of two things. The blue term is a surface tension effect. The red term is a so-called Marangoni effect. So this is the effect that is induced by gradients of temperature that will induce a force, and this is a force that will make the liquid in the melting pool start to rotate. And actually, if gamma is equal to gamma T, so that means it depends only on the temperature, you have a very explicit formulation of this Marangoni effect, and you can see that it depends mainly on gamma prime of T, so the derivative of the surface tension coefficient with respect to the temperature. Okay, so now let's turn to the numerics. We are going to advocate for a multi-physics problem, we are going to advocate an operator splitting approach. So that means to go between the time Tn to the time Tn plus 1, we are going to split the different operators. The first thing we are going to do, we are going to focus on the thermal step. So solving the heat equation without advection in the big domain. In the big domain, the whole metal domain. Then in the second step, we are going to zoom to the smaller domain in which we are going to solve the Stokes equation. And that will allow us to find an approximation of the velocity and pressure, thanks to the approximation of the enthalpy and temperature obtained at the previous substep. And finally, still on the small domain, we are going to solve the so-called advection step. So that consists of all the transport equations. The transport equation coming from the Navier part of the Navier-Stokes, the transport term of the heat equation, and the transport of the characteristic function for the tracking of the free surface. Now that we split, actually you can use the method that you want for each of the steps. So we are going to advocate a finite element method to solve the heat equation, a finite element method to solve the Stokes equation, the Stokes system, and a characteristic method to solve the transport and the advection equation. So let's zoom a little bit. First step is the thermal step, so the heat equation without the convection term. So you have here the formulation in enthalpy temperature, and we are going to put some boundary condition and initial conditions. And then we are going to solve that with so-called Chernoff numerical scheme that will allow us to find a prediction of the enthalpy and the temperature that we'll be able to use for the next step. Once you have this, we are going to go to focus on the Stokes problem. So typically the Navier-Stokes equation without the advection term, again, that we are going to solve in omega n, so the smaller domain, thanks to the temperature. So that means the temperature Tn plus 1/2 will allow us to find this reaction coefficient alpha. We are going to put boundary condition, initial conditions. We are going to use implicit Euler discretization in time and stabilize P1 finite element in space. And that will allow us to find a prediction of the velocity and the pressure in the small domain. And then we are going to move to advection. Just one more thing before that. When you are going to solve the Stokes problem, you need to be able to enforce this surface force here on top of the domain. Again, you're going to have the blue contribution, which is the surface tension effect, the curvature of the free surface, and the red contribution that is an approximation, thanks to the pre-calculated temperature, of the Marangoni effect. Finally, we're going to solve all the advection operators at the same time. So you have an advection equation for phi that will allow us to track the free surface. There will be an advection equation for the velocity v that will allow us to take into consideration the Navier part of the Navier-Stokes equation. And you have the advection of the enthalpy that we removed from the heat equation at the previous substep. And we are going to give boundary condition and initial condition for each of these three. And we are going to solve that with a forward characteristic method that imposes actually no CFL condition. And that will allow us to find the correction of the velocity, phi n plus 1, so that means the new position of the free surface, the enthalpy, so the correction of the enthalpy, and choose the correction of the temperature as well, and then the position of the new free surface, so that means the new metal domain for the next time step. So now in terms of space discretization, what do we have? But now we split, so that means that we can address each of the substeps independently. So to go from time Tn to Tn plus 1, what do we have? First, the first thing that we are going to do some interface tracking that I will not develop in this talk, in order to have a mesh refinement around the free surface in order to be able to more accurately enforce surface forces. And then we are going to move to the thermal step. So on the finite element mesh composed of tetrahedrons here, I'm going to solve the heat equation. Then I'm going to restrict this mesh on the smaller domain, and I'm going to be able to solve the Stokes equation. And then, in order to find the forward characteristic method useful, I'm going to change the mesh and use a Cartesian grid. So I'm going to interpolate from the finite element mesh to a finer Cartesian grid in order to implement forward characteristics. And after, but then you are going to go back, put your variables back to the finite element mesh in order to go back up for the next time step. In real, what do we have? An unstructured finite element mesh of tetrahedrons on which we are going to solve heat equation with P1 finite element and stabilize P1 element for the Stokes system. And then on the other side, we have a structure grid on which we are going to use the method of characteristics. Structure grid is finer, that will allow us to have a better approximation of the free surface. And on top of that, you have interpolation back and forth from one mesh to another, and adaptation in the free surface, which are technical steps that I will not detail. Let's go to some numerical experiment. The first one is a classical one. We enforce a gradient of temperature in the tin melting front. That means that the metal starts to rotate, you have a conductive current, and it solidifies from the right. So here you have an approximation of the velocity on the left and the temperature on the right. To validate our code, we did a convergence study. So we took fine and finer meshes. And then we have here a representation of the solidification front, and you see that if you take larger n, so that means fine and finer mesh, then you have conversion toward the solidification front that actually compares well with the one that you can obtain with another software, for instance. More precisely, if you want to judge convergence, we took the finer mesh as the exact solution, and we calculate L2 errors. Here for all the variables, velocity, pressure, temperature, and solid front position, and you see that for all variables, you have order 1 convergence. That means our algorithm is an order 1 algorithm. This numerical experiment is into the 2D, so it's in a slot, static laser melting. So basically you impose one laser at the top, and it starts to heat, and here you have the representation of the temperature, and but the laser doesn't move. So we consider here some type of steel, and we have a temperature-dependent surface tension that actually depends on this gamma prime of T, as we have seen in the Marangoni effect. And we consider two types of material, actually two types of sulfur concentration in the material that will give us two different behavior for this gamma prime. As for the laser, we impose the laser at the top as a boundary condition on the metal, like a heat flux. So what do we obtain? We see that without moving here, the laser actually starts to melt, so you have a melting pool, and then the free surface starts to move, and you have Marangoni effect that makes the whole melting pool start to rotate, and here you see the velocity streamlines. More precisely, we want to zoom on the free surface. So what we did here, we took fine and finer meshes again, and what you see here are the numerical approximation of the free surface for one given case. And you see that, at least to the eye, you have some type of convergence when the discretization parameter tends to 0. Let's turn to 3D. Same setup, except that now we're in 3D, but we have one single laser source that is static, hitting the metal from the top. In the first part, we are going to assume fixed flat interface. So that means the interface on the top of the metal remains flat. There is no free surface. And what you can see on this picture here is that depending on the sulfur concentration and depending on this variable gamma prime of T, you have different shapes for the melting pool. So that means the key variables here is this gamma prime. But more importantly, now what happens when you allow the surface to move? So we have a free surface. Again, same type of result. Left and right, you have the free surface deformation for the two different types of gamma prime, two different types of sulfur concentration in the steel. More explicitly, I think you can see it at the top. If the gamma prime changes, the Marangoni effect changes, and the shape of the free surface is drastically different. So in the dotted line, you have the very classical shape where you have two bumps on the extremities, but in the bold line, you have one bump in the middle and not in the extremities. So you can have very different free surface deformation. So easy to worse using free surface in that kind of case. So here what you can see, again for the two types of gamma prime, the shape of the melting pool with or without the free surface. And you can see that the curves are actually quite similar. So for that particular case, the static laser melting, it may not be very useful to introduce the free surface deformation. So that leads me to laser polishing. So here what we do, we took a larger piece that is initially very rough, randomly rough, and we are going to make one laser pass actually from bottom to top to try to polish this steel. So this is the mesh. As you can see, it can be quite coarse away from the laser, where we solve only the heat equation, but it has to be much, much, much more fine next to the laser beam. So we are going to do one laser pass. So here, you have the result before and after. Before on the left, after on the right. And you can see that it's initially rough, and after, it looks like it has been polished along the path of the laser. In order to quantify this, we are going to follow the color lines here. So let me show you the profile in the longitudinal direction along the path, but also in transverse direction along the way. So first, longitudinal. What can you see here? So at the top, you have the initial roughness of the surface, and at the bottom, what happens after. So you have something that is much smoother, much less rough, and you can also see that the laser is actually pushing the material in front. What happens in the transverse direction? Again, at the top, you have the very rough surfaces, cuts or transversal cuts. And then after, you can see that it's much smoother. It creates a hole, actually. And it actually pushes the material that solidifies on the border. That is actually a good sign that you need not one pass, but several passes to polish a whole piece. Time for conclusion. I show you a couple model, coupling heat equation with solidification, free surface flow, incompressible Navier-Stokes equation, including Marangoni effect on the free surface. I show you a numerical method that is basically based on operator splitting and a two-grid method. And we have now a standalone solver that is flexible and robust. What are the next steps? Obviously, several passes to see how polished the material can become, and then after that, adding powder to do additive manufacturing. So with this, I leave you with two references, and I thank you very much for your attention.